Thank you. The first thing I'm going to say is I'm rubbish at standing still when I'm talking. So if I go quiet, wave at me and tell me to move back over here. So one of the things that really interests me in our field is the kind of things that are generic. What's the advice that we can take? What are the practices that we can apply that always work? I don't think we have very many of those things. And those are the things that have been interesting me for a little while. And that's really what my talk is about today. So this is the stuff that I hope to cover. What does engineering mean in the sense of software engineering? What are the common founding principles that we might apply that are always going to work and guarantee that if we apply these principles, we will get a better result? And what are those 10 guiding principles that we can follow? And I want to give you some examples and demonstrations of each of those principles as we go through and show how we can apply those to some code and see the impact of that. So my starting point, what is engineering? What is it that we mean when we talk about those terms? Because I think we often get this wrong. I think we often misunderstand that, misinterpret what it is that we're talking about. I think it's a reasonable statement that certainly in modern terms, what we mean by engineering is kind of the practical application of science, what really works. And in other engineering disciplines, if something doesn't work, we stop doing that and we find out something that works better instead. That's kind of what engineering is. So what are those kinds of things for us? I would say that software is one of the more difficult things that we as human beings undertake. It's enormously complicated. It's this weird, ephemeral, fragile stuff, and it has high consequences if a small error happens very often. So how do we get to do a better job of that kind of thing? What works for us? I think a starting point, I've been talking about, I started off my career with jobs with titles like junior software engineer and stuff like that. And we were doing nothing that was even close to engineering, to be honest. I then worked in other places with some of the people in this room where we didn't really like the term engineering very much. And I kind of fell into that. I didn't really like it very much either. And then later I did some stuff that felt closer to what I would think of as real engineering. And I started thinking about, this ought to be an engineering discipline. This is an engineering discipline to my mind. As a result of saying things like this in public, I've got involved in an inordinate number of conversations about bridges for some reason, weird reason. People say, yes, Dave, it all sounds very good, but it's not bridge building, is it? And I think that's usually a complete misunderstanding of what bridge building's about. Because bridge building ain't that easy. So I think we get this wrong. And I think that one of the ways in which we get this wrong is assuming, first of all, that what engineering is some sort of bureaucratic cookie-cutter process. And it's never that. The engineering part of engineering is a creative process. It's a process of learning and discovery. And I'd like to explore that idea in a bit more detail. The other thing that we can definitely say about engineering is it's different in different disciplines. There are certainly some common themes, but civil engineering, building bridges, is different to automotive engineering, which is different to aerospace engineering, which is different to chemical engineering or space engineering or whatever else. Each of these disciplines has its own unique characteristics, its own unique guidelines and disciplines and ways of behaving. So one thing that I think we can be fairly sure of is that whatever software engineering is, it's going to be unique to us in some aspects. The rest of my talk, I'm going to point to what I think are these key behaviours that we need to consider and pull out some examples from different forms of engineering to try and illustrate those ideas. And I might talk about some Lego later on as well. So what does all of this mean for us? What is engineering? This is my working definition. So engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. And I would say that all of those words are important. So it's not enough to build, this is not ivory tower stuff where we're imagining wonderful, Baroque, complex things. It's got to be within economic constraints that match the problem that we're trying to solve. But we need to be adopting rational ways of decision making, making choices based on evidence rather than guesses. To put it more simply, engineering is the stuff that we do to solve the hard problems. These are all fruits of engineering discipline, engineering creativity, if you like. And this is how we as a species solve hard problems. In fact, I would argue that engineering is the foundation on which our high-tech civilization is built. If we look around this room, almost everything in this room, apart from us, but including the clothes that we're wearing, is stuff that's been engineered to some degree. Certainly my computer, the screen, this wall, the chairs that you're sitting on, the flooring, at some level is a product of engineering. It's about applying these sorts of things and making those sorts of changes. So this is the stuff that shapes our world. And I think you can see this. So this is a graph, which this is not my graph, I've copied this from somewhere else, but this is a graph that's meant to show technological advancement. We've existed as a distinct species for somewhere between 200,000 and 300,000 years. So this line goes way back over there somewhere, probably the other side of the river somewhere. But it comes up here, and there's this obviously inflection point here where something happens and advancement, the rate of change of technology just takes off explosively. This is roughly where science started. Here's another graph. So this is a graph from Buckminster Fuller, who was an IBM fellow and a very brilliant man. But he got interested in the rate at which human knowledge grows. And he estimated that in 1900, human knowledge was doubling every century. By 1945, it was doubling every 25 years. By 1982, when he did this research, he estimated that it was doubling every 12 to 13 months. IBM are currently estimating that the whole of human knowledge doubles every 11 to 12 hours. I'm not quite sure I buy that. That sounds a bit extreme, but certainly it's fair that something's going on. So science happened back there somewhere, and computers and software happened around here. We are involved in the industry that is driving this kind of change. There's something happening in our civilization here. So what, if we start thinking about this, what is engineering really for? And I think this is one of the things that we get wrong. As I said, I think that often what we imagine is engineering is about defining some exact solution to a problem. And it's not that at all. It's about this. It's about ruling out the stupid ideas. It's about saying, we've tried all of this stuff and that's rubbish. So all of the solution is over here somewhere. It's within this range of options. And then we've got a choice. We can decide which of these whole range of options to pick from. So it's not about defining the perfect solution. It's about ruling out the bad ideas, fundamentally. If you're of a philosophy of science kind of bent, this is about falsifiability. This is about trying to falsify ideas rather than prove ideas. This is not proving a specific solution. This is about ruling out the idiot solutions. Here's another of those kind of engineering fallacies that seems to infect us as software development professionals. So we seem to imagine, when we talk about engineering in the software context, that it's this kind of bureaucratic, repeatable process. This is about solving production problems. This is about the repeatability, trying to solve a problem where you're trying to create a widget at scale over and over again and get exactly the same result. That's not what we do. bears no relationship to what we do. And it would be stupid if it was what we did, because one of the key elements of software development is this. We come up with a solution of some kind, and that solution turns into a stream of bytes. And one of the unique properties of a stream of bytes, whatever the stream of bytes represents, is that we can reproduce it perfectly for essentially zero cost. So, if we've got a production problem, why? Because that's just a matter of cloning the stream of bytes. We can have 1 billion copies of this thing or 2 copies of this thing for not much difference in the cost, in essence. So we are always doing something new. We are always solving a new problem, because otherwise we just reuse what we already have, because production is free. So we don't have a production problem in that sense. Ours is a very different kind of discipline to production. Sorry, my animation goes a little bit ahead. I've gone a little bit ahead of my animation, sorry. So we can deploy this as many times as we like, and it costs almost nothing. So what that means, certainly for us, I think I'd argue pretty much generically for engineering, if I'm honest. I think that engineering probably represents the peak of creativity of humanity, in my view. If you think about building stuff that explores Mars or goes and explores the solar system, or vaccines that cure us and all of that kind of stuff, they're all engineering. So engineering is about exploration and discovery. Software development, then, is all about exploration and discovery. So if that's the case, what works if our principal aim is exploration and discovery? We need to become experts at optimizing for learning. We need to become really good at that. That needs to be a key focus of the way in which we think about software development and organize ourselves to conduct it. We also we build systems that are beyond the capacity of any single human head. We build them in teams, we build them on massive global scales, we solve problems that are incredibly difficult. So we need to be able to manage that in some ways. So the other aspect of an engineering discipline for software is that we must manage the complexity of the systems that we build. We need to find ways in which we can do that and work sensibly within the scope of our the constrained scope of our understanding and our capacity to be able to do things that go beyond that. And that's one of the other jobs of engineering, to allow us to do more than we can just do by hand or by raw intelligence. For that, I think there are 5 things that are absolutely essential, and these we can kind of think of these as being inspired, at least, by science. Science is the granddaddy of learning. Science is the way that we stop relying on guesswork. Science is how we solve the hard stuff. So we must be iterative. We must be able to try things out in small steps. We want to be feedback driven. We must gather information so that we can determine whether those small steps are heading in the right direction or not. We want to be experimental. We want to have a guess and try out the guess and see whether that moves us forward or backwards and decide what to do as a result of that experiment. We want to work incrementally rather than think really, really hard and imagine the perfect solution to some complicated problem. We want to take small steps and evaluate that each step moves us closer to the goal that we're trying to achieve, and essentially grow our software through a sequence of many, many small steps rather than fewer big ones. And we want to be empirical. We're engineering, not pure science. And so that means we've got to learn from the real world. We need to be able to monitor and observe our systems in production and see how it plays out, and then make choices based on whether they make us enough money, recruit us enough users, run fast enough, are resilient enough, scalable enough, secure enough, and so on. I think that all of these things are essential if we want to target optimizing for learning. We can't compromise on any of these things. So let's look at each of those in turn and see how they are represented in other fields. So this is the Wright Flyer. This is the first heavier-than-air, man-carrying, powered, controllable aircraft. All of those caveats are necessary because there was some version of an aeroplane that did some of those things before. But this was the first one that brought all of these things together and actually worked. Now, the Wright brothers were quite a long way ahead of their competition. It was getting on for about 10 years before there were lots of other aeroplanes from other places. The Wrights almost had the monopoly on flight for a little while. And then things moved quite quickly. But at this, even after that, perhaps for the next 2 decades, these things were death traps. Nearly every aviation pioneer was killed by the machines that they were pioneering in, including one of the Wright brothers. They were extremely dangerous. But how did that evolve over time? Sure, the iteration was slow, but we iterated. So what we did is each time there was a crash, we analysed what went on and we tried to do better next time. Each time we flew the aeroplanes that we built, we tried to figure out how we could do better next time, and we just refined and refined and refined and refined. By around about the time of the Second World War in the 20th century, we got this thing. This is a Douglas DC-3, which was probably one of the first popular, recognisable passenger transport kind of aeroplanes. This was a big step forward in terms of passenger aircraft at the time. Still pretty crude by modern terms. And then we carried, those two had problems. They flew a bit too low. They got too affected by weather, which would crash things, and they didn't have jet engines yet. So we moved on, and we came up with something like this, a modern passenger airliner. In 2017, the equivalent of 2/3 of the population of the planet flew in a commercial airliner, and none of them were killed. That was a first. That was the first time. The statistics say that we in this room are in more danger than if we were sat in one of those aeroplanes. That's ludicrous, but that's what the statistics say. So through iteration, we have gone from something that was a death trap that could carry 1 or maybe 2 people to something that could carry people in their hundreds in a single aeroplane, and where they'd be safer than if they were sat at home. And that's pretty astonishing in terms of what engineering practice is capable of. The thing that's we often think there's kind of an illusion of rigour, where if we imagine that, if we work really, really hard and think really hard and maybe do some maths, obviously that's going to be better, right? Well, not necessarily. Working hard is not the goal. Hitting the target's the goal, and we don't need to have to think really hard. We can apply an iterative process. So one of the remarkable things about an iterative process is that we can hit the goal even if we don't know what we're doing. All we need is that we need a measuring stick. We need a fitness function that will say, are we closer to the goal or further from the goal? And now we can go in a random direction and say, is that closer to the goal? And we can measure that and say, no, it's not. So we can discard that. And we can then move on, and we can try another random go. And we can say, is that closer to the goal? Yes, it is. OK, we'll keep that one. And we'll keep going. And we keep going, and we'll hit the goal eventually. It might take lots of iterations. We discard the things that move us in the wrong direction. We keep the things that move us in the right direction. And eventually, we will hit the goal. This is a much more powerful way of solving problems than just thinking really hard and imagining and doing all of the calculations. Even though it feels a little bit more ad hoc, perhaps. So we could imagine, if we're optimizing for feedback, our measure on the fitness function is the feedback. And that fitness function might be different depending on what the goal is and what we're trying to achieve. Maybe the fitness function is a business thing, so we signed up more users this week or whatever else it is. Maybe it's a technical thing, like the latency was reduced by 10%, whatever it is. But we can use the fitness function to hit the goal, whatever the goal is. Let's imagine that we were tasked with balancing a broom. So how would we do that? Well, we could try the waterfall method of balancing a broom. So we could look at the broom and we could do a detailed analysis of where the centre of the mass of the broom was. And we remember from our early physics training that if we want to balance something, what we need to do is that we need to rotate it so that the centre of mass lines up with the point of contact. So we could do something like this and try and perfectly balance, manipulate the broom so that there was no impulse left that was kind of leaning it one way or another. And we could leave that. If we could get it perfectly still, it would balance, it would work. Essentially, there's one solution to that problem. We have to do all of that stuff that I've just said and get it perfectly right, or it won't work. But that's not how we'd balance a broom. What we do, because that just falls over, it doesn't work, unless you hit that one solution. So what we'd really do is obvious. What we'd do is this. We'd pick our broom, we'd put it on our hand, and we'd start moving our hand in response to the way that the broom tips. So if the broom tips a little bit, we'll move our hand a little bit. If the broom tips a lot, we'll move our hand a lot, and we'll keep the broom balanced dynamically. That's the operation of feedback. This is a much, much, much more powerful way of organising things. This is so powerful that this is the way that rockets work. A rocket does exactly what I've just described in terms of balancing the broom. We've got sensors in the rocket that detect how it tilts and whether it's on track on course. And we've got the rocket motor, which they call it gimbaling. You can direct the rocket motor in different directions to kind of correct the tip. That's the equivalent of moving your hand around. So this isn't worse, this is better. And there are essentially an infinite number of solutions now, rather than just one. So we're much more likely to hit one. It might not be infinite, but there's a lot. Next, incremental. So this is a picture of the first module from the International Space Station. It went through a series of iterative incremental stages of building up to what we get today, which is the thing over there. Now, I'm pretty sure that when they launched this, they had something like that in mind. But I'm also absolutely certain that it wasn't precisely that. There are differences. There are components of that ultimate machine over on the right-hand side that weren't in mind, didn't exist when the first unit was launched. This is how we as a species build complex systems. We build them incrementally, small step by small step. We evaluate each small step and learn from it. We get the feedback and we steer rather than just intuit what the solution is. Next, being experimental. Weirdly, when I describe this to my client base, sometimes they say, oh no, we can't afford to do that, that's too scary. We can't afford to be experimental because we can't afford to be wrong. Well, if you can't afford to be wrong, you can't afford to do anything. I would argue that one of the facets of engineering is that we embrace the idea of being wrong, because being wrong is when we learn things. If I make a guess and I say, this is how that works, and it works like that, I haven't learned anything new. If I make a guess and I try it out and it doesn't work, I go, oh, blimey, I've got to think again now. So now I'm really learning. So what we want as engineers is that we want the freedom to be able to be wrong safely. And in science, that's what we call an experiment. So we're going to organise our work as a series of small, safe experiments to try stuff out, see if it works. If it doesn't work, we do something different. If it does work, we carry on and come up with the next experiment. But we organise everything that way, working experimentally. And I think that goes to everything from the technical things that we do all the way to the products that we put out into production. Nobody knows what the feature set of the ideal product is in software. The users don't know what they want. The product owner doesn't know what the users want. It's all made up. It's all imaginary. And what users know is that when you show them something, they say, yeah, I don't like that. Or, yeah, that's okay. That's about as good as we can get. So what we want is that we want to gather that kind of feedback and we want to try stuff out, including the products, including the ways in which we organise ourselves, including the ways in which we test things, including the ways in which we architect and design things. We want the freedom to be wrong. Without that, how else can we make progress? Because without that, the only thing that we can do is be so brilliant that we always get everything perfectly right. The idea of perfection is an illusion. The idea that our job as software developers is to produce a perfect solution is a mistake. Our idea, what we want is that we want to produce something that's observable that we can learn from. To do that, one of the key attributes of being able to achieve an experimental approach is to be able to control the variables. We want to be able to make a change and see the impact of that change. So we've got to be very specific, very, I suppose, detail-focused on the way in which we organise things. This is where ideas like continuous delivery come in. We build deployment pipelines so we get a reproducible, repeatable process for evaluating changes to our software. If all of the tests pass, it should be a no-brainer, it should be definitive, we can release that into production. But we can only do that if we control the variables so we get a repeatable result every time we run a test or try something out or carry out an experiment. And that takes thought, it takes creativity, it takes ingenuity. Sometimes it's incredibly difficult, sometimes it's easy. But that's what we must do if we're to adopt a more engineering-focused approach to solving problems. Here's an example of that, once again, from the aviation industry. There's been a long process that's been in place in engineering aeroplanes where you'd never fly. If you want to create a new aeroplane with a new engine, you don't fly them both together. What you do is that you get an old aeroplane like this, you take the engine off and you attach the new engine to the old aeroplane. And then some brave person goes and flies it. And if they come back alive, you say, that's okay. So now we'll move on to the next stage. So now you get the new airframe and the old engine. You go and fly that. Some other brave person probably goes and flies that, tries it out, see if it all works. And if it does, only then do we fit the new engine to the new airframe and fly it all. That's how you make progress. That's how engineers make progress. We try stuff out, we see what works, and we keep the stuff that works, and we discard the stuff that doesn't. We also need to be empirical. So this is another aeroplane. This is the first production jet aeroplane. The jet engine was a British invention, but the Germans built the first production jet aeroplane. It is a Heinkel, and it was built during the Second World War. Now, you can see that this looks kind of unusual compared to a modern aeroplane. And I'm a bit of an aviation nerd, and what this is called a tail dragger arrangement, which means that you've got this little wheel at the back and two big wheels at the front. And the reason for that design choice is that when you have a big propeller engine, you need room for the propeller at the front. And so that was how nearly all aeroplanes looked at the time when this was built. So they built this aeroplane, and then they put a jet engine in it, and they melted the runway. And so after that, they thought, oh, okay, we probably shouldn't do that. So pretty much all jet aircraft since then have a different undercarriage arrangement called a tripod, where you've got these big wheels a little bit further back and a nose wheel at the front with the centre of gravity in front of the big wheels instead of behind it, so that it sits horizontal to the ground. The jet's not pointing at the runway, it doesn't melt the runway. This is another practical example of empirical learning. SpaceX are a continuous delivery company, not just in terms of the software, but in terms of the hardware that they're building. They're currently applying the kind of empirical learning that we're talking about on a massive scale. They're blowing rockets up almost monthly. but they are also the most successful rocket company ever, with repeatable reusable rockets in the Falcon 9 system of tens of flights reusing those rockets and dramatically reducing the cost of getting hardware into space. One of the nice, just in terms of the software, SpaceX use full-blown continuous delivery for their software too. They have deployment pipelines, trunk-based development, TDD, all of that stuff. And they are updating the software to a Falcon 9 rocket 40 minutes before a launch. So if all of the tests pass, it's pushed to the rocket. This is a rocket that carries people to the International Space Station. So if people complain you can't do continuous delivery for safety critical systems, the other aspect that we started talking about is just how complex modern software is. The picture that labelled Amazon.com, that's a picture of microservices in the Amazon estate. This is a little bit old, and I have seen a movie of this, and it looks like an organism because it's dynamic, it's moving all of the time as new microservices are introduced and old ones are retired. Amazon pushes change into production at the rate of 1.5 changes per second. Modern software is complicated stuff. So, as well as optimizing for learning, we need also to optimize to manage complexity. And the ways in which we can manage complexity, another 5 things. And these are all things that you will be familiar with if you've ever touched any software. These are ideas that think, yeah, okay, motherhood and apple pie. But I'm not just saying, yeah, these are nice, these are good. What I am saying is that if we want to adopt an engineering discipline, always prefer the choice that maximizes these things. Whatever it is that you're doing, always prefer the choice that improves modularity, cohesion, separation of concerns, abstraction, and coupling, is my advice. So let's look at each of those in turn as well. So first, modularity. So yeah, yet another aeroplane picture. I like aeroplanes, can't help it. So obviously, we have the engine separate from the airframe, as we'd already discussed. It means that a different company can build that engine. We can treat it independently. If there's a problem with the entertainment system on board the aeroplane, doesn't mean that the engine's going to stop. That's probably a good idea. There's definitely software that we're all familiar with that doesn't sound like that, right? So modularity gives us a lot of nice choices, a little bit closer to home. This is a modern iPhone, and even this highly integrated, amazingly engineered device still has a series of discrete components, each of which is focused on solving one part of the job and is distinct from the others. This is still a modular system. It might be a highly coupled modular system, but it's still a modular system. That's how we solve hard problems. A bit closer to home. You can tell by looking at me, I'm old. I'm probably one of the oldest person in the room. Sorry, I just saw you over there. just a joke. I am probably the oldest person in the room. When I started writing software, if we wanted to print something out, we had to know which printer we were printing to. We had to write the code, and the codes for an Epson FX80 was different to the codes for an Epson RX80. That's how specific we had to be if we wanted to print something out from our code. Sometime later, operating system vendors came along and said, this is stupid, let's try and help with this problem. So they came up with an abstraction for printing. And that abstraction gave us a line of demarcation between the applications that needed to print and the things that did the printing. And then they could translate to the specific printer. So we came up with the idea of printer drivers. This is not a new idea, but this is how we solve difficult problems. And that meant that now I could concentrate on the bits of my code that were important to me rather than worrying about the bits that were important to the printer vendor. Here's a piece of code. This is a not very modular piece of code. So there's this if statement. So let's have a look. So this is 361 lines in an if statement. The commonest comment that I get when I show people this piece of code is, oh, we've got much bigger if statements than that. So let's have a look what that looks like in the context of the code. So there's this fairly horrible looking function in the first place. And yes, this is written in C, but just because you're writing C doesn't mean you have to write crap code. But here's my three. So if I only did this, looked at this, so let's see, it's if unlikely bang CI. Everybody clear what that's doing now, yeah? I saved you the trouble. I spent a little bit of time trying to read this code and trying to understand what it was trying to do. I think that what it meant was this. If there's no connection, CI, create a connection. And when I looked in the areas of the code around this, there were about 3 or 4 other places that looked rather like this to me. I didn't look exhaustively because I was bored by then. But you know, I could have got some reuse if that's the case. So what would happen? So just that simple thing, that's a move in the direction of better, more modular code. Just that one step. We're not necessarily talking about separate modules in different files. That's certainly a thing, and it's certainly a useful technique. But just this is also a version of modularity. And that's better code, right? My favourite description of what good design is in software comes from Kent Beck. So good design is about moving the things that are related closer together and the things that aren't related further apart. But I think it's funny, but it's also kind of deeply true. So the things that aren't related further apart is modularity. The things that are related closer together is cohesion. It's a bit of a flippant way of describing these deep concepts, but principally that's it. So what we're trying to do is that we're trying to organise our code better. So it's easier to understand, easier to read, easier to work on. The next is separation of concerns. This is a little different to modularity and cohesion because I think of this more as a kind of technique that allows us to get to better modularity and cohesion. So the idea of separation of concerns is that we want each part of our system to be focused on doing one thing and doing that well. This is a modern electric BMW, and BMW have made a design choice in the electrification of their cars. What they've decided is largely they're going to build all of their electric cars on one platform. So they're going to separate the concerns of the utility of the vehicle from the concerns of the drivetrain, the batteries, the charging, the steering, the braking, all of that kind of stuff. So if you want a SUV, you buy the same platform with an SUV shell placed on top. If you want a sports car, you get the same platform with a sports car body on top. This is separation of concerns. And it's useful. It means that we get reuse, we're able to invest more time and energy in one part of the system and get advantage from that. Here's another car. This is my favourite car in this picture. This is obviously a very early car. And if you look at this, there's not very much abstraction going on here. If you're of a mechanical mindset, you can kind of work out what's going on here almost everywhere. It's really interesting. So this thing here is, I think, a combination control of accelerator and braking in one stick. You push it forward and you go faster, you pull it back and you go slower. I think that's what it's meant to be. And then this thing over here that looks like a tiller is a tiller. So what's going on there is it turns that tube and rotates that tube, and that goes down. There's a little crank at the end and a little push rod from the crank to the front wheel, and that turns the wheel. So you can kind of see what's going on. It's obvious, but there's no abstraction going on here. So what happened over time, we started to, instead of doing that kind of thing, where each car was unique and specific to the manufacturer, sometimes specific to the model that was being manufactured in terms of the controls and everything else, over time we started standardizing the controls. We started abstracting the controls from the way that they work. So we got to a steering wheel fairly quickly, although this is still an old-fashioned one. It's got a weird control in the middle, which I think is for mixture in the engine. We got rid of those. And then we carried on iterating. We kind of tried out new things. And ultimately, we get to something like this. This is a steering wheel in a modern car. Now Who can tell me how that works? No one. We don't know how that works because it's abstracted the problem from us. We don't need to know how it works to be able to steer the car. So it could be that it's parallelogram steering. It could be, so it's mechanical. It could be rack and pinion steering. It could be power assisted. It could be something like that over there where we got hydraulic steering. Or it could be modern electric steering. It could be rather like a game controller where there's just a voltage that's being sent to servo motors that actually move the wheels. We don't know. We don't care unless we've got to fix it. But we don't really care. So another way, let's start talking about some code. So here are two pieces of code that are talking to each other. And the blue one's going to initialize the orange one, which is going to return a message saying that it's been initialized. It's going to get a delivery date and deliver the delivery date, and so on and so on. This is horrible, right? This is nasty. It's not even clear what's going on. So a nicer design would be something like this. It would be if my clicker worked. So we could say place order, order place. We've raised the level of abstraction. It's now clearer what the conversation's about. All the same stuff's going on, but it's going on in different places. We've got a conversation that's easier to reason about. We can talk about this kind of interaction with a business owner if we want to, because the conversation's clear what's going on. We want each part of the system to keep secrets from other parts of the system so that we can change one part without that change leaking to another part. Last of my 5, coupling. I said there'd be Lego. So here's 2 sets of Lego. I am the very, very proud grandfather of 3 gorgeous grandchildren. And my 2 young granddaughters, the boys too little to play Lego yet, but the 2 young granddaughters play with Lego like this on the left to me, and they'll build something and they'll show it to me. I'll say, "Oh, that's wonderful, darling. What is it?" and they'll say, "It's a giraffe," or "It's a spaceship," and say, "Oh yes, it's a wonderful giraffe," and all of that kind of thing. The thing with a system like that is that they're there's definitely coupling. You can't get a system that works without coupling. They fit together. But it's loosely coupled in the sense that we can rearrange those in a whole variety of different ways and come up with different solutions. We can build a spaceship or a castle or a giraffe or whatever we want with those sorts of things. This thing is very, very different indeed. This kit builds one car. It builds a Ferrari. If you want to build a Maserati, you need a different kit. This is precise. I can't put these pieces in different places. I can't build a submarine, let alone a giraffe, with this kit. This doesn't mean that this is wrong, just means that it's different, less flexible, less powerful in some ways. There's a trade-off here. There's a trade-off in terms of the standardization, the quality of the output to some degree between the two. But this more loosely coupled thing is more flexible. So I don't recommend loose coupling under all circumstances. My recommendation is managed coupling with a preference towards looser coupling where you can get away with it. You want it to be as loosely coupled as you can get away with. If you want to build a Ferrari that's exactly like that, you probably can't get away with a loose coupling. But for most systems, there are places where you can have loose coupling and there are places where you don't. So let's look at our blobs again. So let's just imagine that we've just updated the orange one. We've just changed the internal date format to a better representation. And we could, if we did this as before, then when we return the delivery date, that's going to break the blue one, because the blue one doesn't know about the new delivery date. And the blue one was talking direct to the database of the old one, if you notice the picture. So it's broken that as well. So we just destroyed our system because of the coupling between those pieces. This is very, very common, particularly in legacy systems, this kind of backdoor integration. So what if we were using the kind of abstraction that we talked about before and we managed the coupling between the two? So now, because we've got a more clearly defined conversation going on, a more abstracted conversation between the two pieces, we could do this place order. And now I've put this little extra bit in my picture. This is kind of representing ports and adapters, so it's kind of hexagonal architecture. So now what we could do is that if we decided to, we could release a version of the Orange service that understood both version 1 of the date format and version 2. And depending on the format of the place order, the version of the place order call, we could respond appropriately. So now we've insulated the blue one from changes in the orange one. That's a better design. That's a more flexible design. That's what microservices are supposed to do. This gives us the freedom to change things in one place and not affect other places. So I want to kind of wrap up. I'm running over time. Are we okay to run over five minutes or so? So I want to talk a little bit about how this applies to code. And here are my 5 things for managing complexity. So not just motherhood and apple pie. These things I'm recommending as specific guidelines. Make choices based on maximising these things. And so here's my example. So I want to write a car. So here's my car. It's got an engine. When we call start, we're going to put it into neutral, apply the brakes, and then start the engine. So let's write a test for that. So we're going to create a new car. We're going to say start the car, but there's nothing I can assert unless I decide to do something dirty like brake encapsulation so I can get at the engine up there. Then there's nothing that I can do. This is not testable code. So now all I'm going to do is change my design approach to make this more testable. And I want to see the impact of that. So if we want to make our code more testable, the obvious place to start is by writing a test. Because now we're going to be forced to design code that's more testable. So here's my start. Should start better car engine. So I'm doing here what I often do when I get stuck, is that I write the test backwards. So what's the thing that I want to assert? Well, what I want to say in the end is that the engine started successfully. So that's my assertion. That's the outcome that I'm hoping to observe. And I want that to be true when the car was asked to start. And then in order to do that, what I need is that I need access to the engine. So I'm going to create my better car by injecting the engine. Yeah, we're just talking about dependency injection. And I'm going to create a fake engine that allows me to recover the result of whether the engine was started or not. Here's my fake engine, just in case you doubted me. It doesn't do anything very interesting. We'd probably use a mocking library or something like that to do that in reality, but it's easier to show you the fake engine than teach people that have never seen it mocking. I'm not saying you've not seen it, but some people don't. So here's my better car. We've injected the engine, and we're storing that as a private member variable, and we're interacting with the engine here to start the car. So that's going to make the test pass. So let's look at the impact on our design of simply making it more testable. So the first thing is, as we said, the only difference between these two cars is the dependency injection. And there's more to test-driven development and its impact on design than only dependency injection, but dependency injection is a big win. Dependency injection is a way of introducing measurement points to our code to allow us to evaluate what's going on in our code. So that's a good thing. But look at our design. So went ahead too fast. So there's our better car. So what's happened? Well, this code is more modular because this code knows less about petrol engines than it knew before. It's more abstract because it knows less about petrol engines than it knew before. It's more cohesive because all of the code here is to do with the car and the absolute minimum degree to which it interacts with an engine. And it doesn't know things about how to create a petrol engine and all that sort of stuff. If that was more complicated, creating the petrol engine, this would be much more deeply coupled to the petrol engine than before. So it's more modular, more cohesive, has better separation of concerns, fairly obviously, because all of the engine stuff is somewhere else, or the car stuff is here. It's more abstract, and it has reduced coupling. Only, I did nothing else other than make this code more testable. That's all. So test-driven development amplifies our talent as a designer to design better code. The result of that is that in production, if I want to use my better car, I could create a petrol car as before, and it's exactly the same in terms of behaviour as it was before, but it's better. It's a better design, because now I can also create a car with an electric engine and reuse all of that code. This is more modular, better designed code. More useful. It has more utility in terms of our use in real applications. If I was some kind of crazy person and I wanted to create a car with a jet engine, I could do that too. So I want you to. I am just overrunning, but you said I got 5 minutes longer. So I'm nearly done, but I want you to just pause and just do things. Think of a project that you're very familiar with, something you're working on now or something that you worked on recently. And imagine two versions of that software. So one version of that project, you didn't iterate, there was no feedback, so you weren't any learning, it wasn't incremental. So basically, you had to think really, really hard and get everything perfectly right first time. There was no experimentation. You weren't trying things out to see whether they worked or not. No empirical learning after the fact. Well, probably there might be some empirical learning because you'll put it into production and everything would fail. And that's kind of an empirical discovery in its own right. But just imagine that, and then imagine a system where you were doing all of these things. Each small step, you were evaluating them. Each one, you were getting feedback and understanding whether this change was good or bad and moving you in the direction of your goal or further away from it. And you had the ability to experiment, to try things out, trial and error, see whether it worked or not. If the feedback's fast enough, you can try anything out. And if all your tests don't pass, you back it out and you try again, try something new. Which project would you rather work on? Now imagine, do the same thought experiment with the other one. Imagine a system where there's no modularity, no cohesion. There's bits of the VAT calculation spread all through the code all over the place. No separation of concerns. The whole lot is in one place. There's no abstraction, no seams of division between one part of the code and another. Tight coupling everywhere. This is so common that we've got a name for it. This is a big ball of mud. This is incredibly common. I'm sure all of you have seen versions of code that looks like that. Now imagine something that is more modular, more cohesive, better separation of concerns, more abstract, with managed coupling. You'd rather work on that version as well. And I've said nothing at all about programming language, framework, problem domain, industry sector, regulatory needs, anything. This is generic. This works for every kind of software in every domain across the board. This is what engineering looks like. These are engineering principles. If we follow these, if we always prefer these things and organise our work to prefer these things, we will get a better outcome. I think we can say, and we have quite a lot of evidence for that as well. The evidence, I'm not going to cover it now, but look at the DORA metrics. Fundamentally, though, all of these things matter for one reason. They allow us to change our software easily. I would argue that ease of change is the defining criteria for quality in our software. Now, that might sound weird. Of course we need systems that are secure. Of course we need systems that are scalable. Of course we need systems that are resilient. All of these things. But if we can't change the software easily, how do we get those things? If we can't change the software easily, the only way we get those things is getting them perfectly right first time. And that's just not going to happen. Nobody is that good. That's an illusion. So we're going to need to iterate, experiment, try things out, learn, adapt, reflect on our adaptation, make more modular choices, and all of those things. They all make the software easier for us to change. So optimizing for ease of change of our software is how we get quality for our software. That's how we measure it. How easy is our software to change? I had the privilege of interviewing Kent Beck not very long ago. I'm not a person who has heroes, but he's close to me in terms of a hero. And I think it's close to a statement of a genius when he said in the subtitle of his book on extreme programming, "Embrace change." We need to embrace change. We need to assume that change is normal. We need to assume that making mistakes is normal. We need to be able to change our software. We need to be able to design it to be easy to change. We need to be able to architect systems that are easy to re-architect. That doesn't mean over-engineering solution. It just means compartmentalizing things, using lines of abstraction so that we can talk to one kind of data store or replace it with another without too much difficulty, maybe. The quality of our system is defined by our ability to change it. And with that, I'm done, and only slightly over time. Thank you very much indeed.